Okay, so let's return. For now, ignore this thing. I will get to it in 2 minutes. Okay. So last time what we saw the adjoint of a linear map on an inner product space. V and of course with V finite dimensional over a field which is R or C. Okay. So V is the inner product space over R or C, and then the point is this satisfies T. So let's say V comma T. Sorry. Yeah. Okay. T star V comma W equals V comma T star T. T star V comma W is equal to V comma TW for all V and W in V. This was the sort of defining equation. In fact, basically this can be taken to be the definition of T star as well if you want. Anyway, this is what we saw last time. Okay, now the theorem we want to prove is the following. Okay, given again the same, given V finite dimensional, so say V is inner product space, finite dimensional over R or C as usual, and T is a linear map from V to V. Okay, T is linear map. Then so you can B is a ordered. So let's say first I'll call the term orthonormal, and the reason for this orthonormal is going to be explained in this roughly in this slide. Orthonormal ordered basis. Ordered basis of V. Then what do I know? I know that I want to look at the matrix of T star. I can do this. This is equal to the following matrix. Oops, I forgot to use this one. This is equal to, take the matrix of T itself first. Okay. So this is a square matrix of, I don't see where to put this. Then I'll put it here. The matrix of T star. What I can do is the following. I take the matrix of T, BB. I take the transpose of this matrix and I take the bar. Okay, so this is the conjugate transpose or the transpose conjugate of the matrix of T. And because of this definition, so this is for any square, this is of course for square matrices, but regardless, because of this definition, we impose a new definition. Okay. The definition we impose is that V star, so sorry, for any matrix, so for A belongs to C to the M cross N, and I don't care if M equal to N or not, so M can be equal to 1. 1 cross N is just a column vector. No, 1 cross N is a row vector. It can be N cross 1, which is a column vector. It can be 1 cross 1, which is a scalar, or it can be M cross N, any. It's for A. Define the adjoint of A to B. You get the idea. It is exactly this matrix. This formula. A star equals A transpose bar. You could also just take A bar and then transpose. It doesn't matter, right? It's the same answer. Okay, so this is the definition arising from this theorem. So why is this theorem true? Okay, and to answer this thing, I want to so basically I want to understand first of all. So the proof of the theorem, we first make a claim, and this claim is what I'm trying to explain in this box here. Okay, the claim is the following, okay? And I'm crucially going to use the fact that this ordered basis is orthonormal. So suppose the claim is, suppose I want to calculate the ijth entry or the ijth entry of T. Okay. So given any linear map, I don't have any restriction on the linear map. So given T, if I want to calculate the ijth entry of PBB, then this is exactly equal to VI and TVJ. Okay, this is not obvious, and that's what the whole point of that box is. Let us discuss why. This is the first step. This is sort of the most important part of this theorem, is this observation. So maybe this observation should have itself been the lemma in its own right. We will just call it a claim. Now, why is the claim? Why is it that the ijth entry of a given linear transformation on an inner product space, why are the entries equal to this? Okay. So yeah, let's say that. Okay. So why are they equal? So now let us recall how we compute. Suppose I have a linear map without an inner product. Suppose I don't have an inner product. I have a linear map from a vector space to another vector space, both finite dimensional. How would you compute with respect to some ordered basis the entries of that matrix? So let's remind ourselves how we do that. Okay. So this is the diagram. So recall, given T from a vector space B of dimension n to a vector space W of dimension m over a general field, not R or C, any field, any vector spaces, no inner products. Okay, so V and W are finite dimensional, and let's give them ordered basis. So V1, V2, Vn for V, W1, W2, Wn for W. Okay. Suppose these are ordered basis. Now, then how do you calculate the matrix? Well, the matrix first of all takes f to the n to f to the n, roughly speaking. So it must be m cross n, and so I will index it by the m basis first and the n basis next, and aij. I goes from 1 to m and j goes from 1 to n. Right? And this matrix is given by the standard well-known formula. TVJ equals summation aij wi. Right? Take the jth basis vector in the input, apply the transformation, you get a vector in the output space. Therefore, it's a unique linear combination of the basis, chosen ordered basis. Those scalars, those coefficients are exactly the matrix entries. That is the definition. Okay. Now suppose B star is the dual basis. So how do you recover? I have this vector. From here, how do I recover the aij explicitly? I use the dual basis. So suppose take the dual basis of in W star to B prime, to this basis of W. Dual basis, what does it mean? It just means that this happens. Right? That's what dual basis means. If and only if phi I of Wj is delta I. Maybe I should say phi j of Wi. Why not? Let's say phi j of Wi. Yes, is delta ij, right? And either way, it's the same. Delta ij, delta ji. Okay. Then aij. So what happens? I look at this vector here. I apply. I just want to isolate the I coefficient, so I just apply phi I. Then I get aij is phi I of tvj. That's what it is. Right? So that's all I do. Actually, maybe I should just keep it as phi I of wj. Why not? It doesn't, and it really doesn't matter if I use I and j here or j and I here. Okay. So that's what I'm doing here. Now, in this case, what are we doing? We are still having a tvj, but we are applying not phi I, but vi bar. So vi, the inner product against vi. So the real question, so to prove the claim, let me close the box here. Okay, so the proof of the claim. So to show the claim, we want to use, what is this? This is, we are trying to use where is the other pen? We are trying to use Vi and this in place of phi I. Right? Because we are applying exactly this linear map to tvj. So the question is this the dual basis under the given assumption of B being orthogonal? And that is exactly why you need. So when is this? When is it the case? For which kind of basis? So now, okay, now we are showing the claim, which means we have come back to the setting where V is a finite dimensional inner product space, B is an ordered orthonormal basis, and W is the same as B, B prime is the same as B. W and B. Okay, so here W equals V, B prime equals B. Okay, and we are asking when is it that these functionals, these as we said last time in last class were functionals. So when is it that these functionals are indeed the dual basis to the VIs. So now note that. So note that. Now note that. So VI and this thing is the dual basis to the VJs to B. B is V1, V2, Vn. I did not say that here, or did I? Oh, sorry, I should have said that here maybe. Where V equals V1, V2, Vn. Okay? So this is the dual basis to the same thing. If and only if and only this holds, that's the definition. Vi Vj equals delta Ij for all I and j. That's the definition of the dual basis. But what does this mean? It means that if I and j are not equal, then these two must be orthogonal. And if I and j are equal, then you get a non-square of Vi must be 1. So indeed, it's exactly orthonormal, and that's the assumption. Therefore, the claim holds. And sorry, if and only if B is orthonormal, which is true. By assumption, so true. So this is why the claim holds. The claim is that the IJF entry of any matrix with respect to an orthonormal basis is just Vi, comma TVJ. Earlier you would have to say it is the phi I of TVJ. You would have to say it is phi I of TVJ. But the phi I is the dual basis, and that is exactly Vi, comma dash. Because the basis is orthonormal. That's okay. So now once you have this, now after the claim is proved, the theorem is very easy to prove. So let's prove the theorem. So proof of the theorem given the claim. So this shows the claim, and now returning to the proof. The theorem okay, now let's return to the proof of the theorem. Now it's not that hard. So let's actually calculate. Now we just need to calculate the entries. So what was the claim? The claim was that the entries, the T star matrix is the adjoint, the conjugate transpose of the T matrix. Let's start. So T star BB. Let's write down the jkth entry. Sorry, ijth entry, I guess. Okay. Now what is this? Because of this formula, this is equal to Vi and then T star Vj. But now because of the definition of the adjoint or the linear map, this T can be taken here. So you get TVi Vj. But now again, I flip them back using the inner product. Vj and then TVi. But I must take a conjugate. And now what is this? Without the conjugate, by the exact same claim. So this was from the claim. And this again is from the claim. Oops, not conjugate, but the claim itself. By the claim, what is this? This is exactly T, BB. But now it is Ji. and then and that is exactly the right hand side. This is exactly PBB transpose conjugate. Now, because I've taken the transpose, the JI becomes IJ. And therefore, the right hand side equals the left hand side. Okay? So that is the end of the proof of the theorem, which allows us to, or which motivates naming the adjoint of a matrix for the conjugate transpose. And the justification is because we have to understand that the dual basis in this inner product space situation is exactly this basis here. Okay, so that's the end of the theorem. I will now erase this written on board and we can continue. Okay, so yeah, 1 second. Okay. So now basic properties of adjoints. Maybe I should just use a new pen and save myself some trouble. Let's call it proposition or something. 1 second, sorry. Sorry. So now again I have a finite dimensional inner product space, linear maps, and you can write down some properties. Say V comma dot this thing inner product is finite dimensional. Again over the real numbers or complex numbers only. And let's say I have two maps, T and U are linear maps from V to V. Okay, so one, T plus U star. So I can write down all these maps. So T plus U adjoint, T adjoint, U adjoint, and of course, as you can expect, it is exactly what it should be. Second, if you look at any scalar multiple, say C belongs to F. If you look at any scalar multiple and then the adjoint of that, again, that is pretty much what you expect. You take the conjugate transpose, so the scalar also conjugates, and then the conjugate transpose. Okay, what else? You can then also you can compose, because these two maps are there. I can talk of the composite. So I can take first U and then apply T. So it's written in this order, but that means first U is applied, then T is applied to a vector, and that is exactly the same as U star composed with T star. So just basic properties, right? And the last one is of course T star star equals T. Okay. So again, these are very standard using the definitions of the adjoint map, the defining property, that same inner product property. So I'll do only one of them. I think I'll do the third one. So you can do either. You can either use a fixed orthonormal basis. So proof, I'll just say the proof here. Either. So the point is these matrices, so if I wrote down these things for matrices, then the statements are incredibly trivial to prove using the property of conjugates and transpose. This is obvious. Like, A star star is A transpose conjugate. And now because transpose and conjugate this can be exchanged, I can take conjugate again and then transpose. But taking conjugate twice is the same as saying nothing. So I'm just doing A transpose and then transpose. But taking transpose twice is also doing nothing. So I get it. So if I were looking at matrices rather than actual linear transformations, then these proofs are trivial. So you can first of all either work with matrices. How do you work with matrices? Because of the proposition. You can make because of the theorem. The previous theorem, the preceding theorem, and a fixed orthonormal basis, obviously. Or you can work directly and prove it using the defining property of the inner product, using this property. Or or work directly. For example, 1 second. Yeah. Okay. Oh, great. Or work directly. For example, let me do number 3. Why is statement 3 true? So, for example, statement 3. So, how do I show this? How do I show that linear transformations, two transformations are equal? You show that if and only if, when you evaluated all vectors, you get the same answer. And if and only if you evaluated all vectors and all functionals, you get the same scalar. So, well, so given let me calculate V and then T composed U star of W. Well, so on the one hand, this is T composed U of V and W. Sorry. I have a diagram below. This is so the definition of any star is that you keep the non-star version here and then write down W. But now what is this? This is literally T of U of V and W. So we have T U V W. Right? But now because T is here, I can take it on the other side. U of V, T star of W. And just the definition of T and T star is used once, twice, and thrice. Okay, I'm this right now. Okay, and what is this? This is exactly now the U is here, so I can take a U here. V and then U star of T star W. And because this holds for all V and W, let's see, since this holds for all W, first of all, what we get is that, since this holds for all V, we get that T composed U star of W equals U star of T star of W. This is by the homework, by some homework, right? That is against every inner product, some vector, this minus this. So this vector minus this vector against every V is 0. Therefore, by the homework problem, as homework 11 itself, or maybe 10, these two vectors must be equal. So this minus this equals 0. So this equals this for all W and W. All W in V. So there is no W. But then that means, well, these two transformations, let me even rewrite this as U star composed by T star. But that means that these two transformations agree at every point. Therefore, they are the same transformation. So yeah, so you can either proceed directly just using the defining property of stars of the adjoint, or you can use the fixed orthonormal basis and therefore prove the other. It's either way. Okay, great. So that is that. This. And you can try the others as well. Okay, great. So that is done. Okay, so that was the end of the adjoint section. Now let's move on to the orthogonal and unitary maps. So a natural question, I'll start it here itself. Linear maps. Of course, they're always linear. This is a linear algebra class. The question is the following. Which are the maps, which are the linear maps which preserve the length of a vector, of every vector, or which preserve the inner product? So basically, which linear maps? Preserve the norm or the inner product, or maybe or even the inner product. What does that mean? It means i.e. TV, let's say norm of TV equals norm of V for all V in the inner product space, or norm of or the inner product of TV and TW equals the inner product of V and W for all V in V and W in the. That's the question you're asking. Which linear maps preserve this? Okay. So great. So that's the question. Let's maybe directly answer it. Yeah. So okay, no, maybe I'll give you two examples. In the most standard inner product space you're used to, the plane. So for example, let's say F is R, and V is R2. And let's look at some maps. So one map, for example, is the rotation map. So take any vector and rotate it by an angle of theta. Let's say counterclockwise. Oops. Clearly, this is a badly drawn picture. Yeah. You can check that this rotation preserves lengths. In fact, it also preserves the inner product. Okay. Another map is reflection. Let's say reflection about, I could reflect it about any axis. I can reflect it about this axis. And T of T theta of V is the rotation by angle theta. I'm not writing down counterclockwise. And then, or this one is just, or T n of V is reflection about the line y equals mx. So both of these things are actually things that of course preserve the length and the inner product. Are examples of maps which preserve length. Okay. Let's call this T prime just to be safe. Which preserve the norms I mean the point is if I take W equals V here, then I get the norm square of PV equals the norm square of V. And then I take the square root, I get the first one. So preserving inner products is a stronger condition. It implies preserving norms as well. Therefore, I don't need to even say preserve norms, but it does preserve inner products in fact. Okay. These are both examples in R2 in the plane. And with this background, let us write down the theorem. Again, and this time I don't need a I don't need a finite dimensionality. It's over any inner product space. So, and real account. Let's just say let's say so the is an inner product space, so I won't even say that. Suppose T from V to itself is linear. I think I just want to say the following are equivalent. The following are equivalent. TFAE stands for the following are equivalent. The first is that it preserves norms. The second is that it preserves inner products. They are both if and only if. Yep. And the third is that T satisfies by itself without any vectors around. T times T star, or T composed with T star, or T star composed with T is the identity. Okay. Or T star composed T. So both of these. Okay. Why is this true? So let's prove this. Okay. So okay, first of all, as I already told you, why 2 implies 1 is trivial. So let's finish that first. Set W equals Z and take the square root. 1 implies 2 is very interesting. And this is going to use some very nice identities, and that's why it's worth stating. The point is, okay, first of all, obviously, as we've already said many times, to discuss statements in norms is harder than to discuss statements in norm squares. And that's exactly the point. So, so recall that I'll just say we use, so I'm going to use, we use the polarization identity. We use the polarization identities over R or C. And there are two cases. The identity for R is different from over C. So let's do the cases. So F equals R, first of all. What we are going to say is the following. The identity states that the inner product of V and W is equal to 1/4 non V plus W square minus non V minus W square. Okay? And basically this is just saying, you know what it says. It's A plus B square plus 2AB. 2AB is 2V inner product W minus A plus B square minus 2AB. So you get a 4AB. Well, here you get 2 inner product of W. Actually, so here you get inner product VW plus inner product WB. Here you get minus inner product VW minus inner product WB. But because this is over real numbers, VW and WB are the same because there is no conjugate. Therefore, you get plus 2AB and minus 2AB with a minus sign. So plus 4AB by 4 is 8. So I'll leave it to you guys to check this. This is so obvious. The complex version, the complex polarization identity is actually a homework problem. But the real one is so trivial that I won't even ask you to check. Well, maybe I'll ask you. Fine, also. So add to homework. Let's see. Okay. Now, how does this help us? Well, so now 2 implies. Now, if 2 holds, sorry, we want 1 implies 2. So if 1 holds. I should have mentioned, by the way. Here is where I should have mentioned the definition. Such a matrix, such a map T which satisfies either 1, 2, or 3 is called the unitary map. Such a map T is said to be unitary. And if the field is R, then it's said to be orthogonal. So it can also be said also or usually orthogonal when or if F equals R. Okay, so it's said to be unitary for complex numbers, complex field, and orthogonal for the real field. You can also say it's a unitary real matrix, but unitary real matrix is just orthogonal. Okay, so now let's say 1 holds. Then let's calculate. So let's look at the left hand side of 2, TV and TW. First of all, by this polarization identity, it's 1/4 of TV plus TW square minus tv minus tw square. Right? But now t is linear, so of course this is 1/4 of t of v plus w. And this is t of v minus w. But now you see, this is where I use property 1. T of any vector is the same as norm of that vector itself. So I can remove the t from both of these and just say v plus w square minus v minus w square. And now that again by the polarization identity is exactly the inner product of v and w. And because this is true, well, that's what we wanted to do. That's what fine. So that is property. That is how 1 implies 2 over the real numbers. Over the complex numbers, it's exactly the same thing. So f equals c. I will write down the polarization identity. Use instead. I will only write down the polarization identity. I will not write down this proof because it is identical. So that, but the polarization identity itself is not the easiest. So let's write this out. Okay. So VW. See, I think you can see this. Yes. Again is 1/4. But this time it is slightly different. So this time you say it's d plus w square. So there are the same two terms as above. Minus v minus w square. And then there are two extra terms with imaginary roots. Minus I v plus iw square. Remember, I is the square root of minus 1. Plus I v minus iw square. And once you have this, then you proceed as above. This shows why 1 implies 2. So again, the proof is not over yet. So this is the proof of 1 implies 2. And again, as I said, so this is homework and this is also homework. And I should point out, this is your last homework set for the course. It is, I will assign it today, Wednesday, and it will be due next week. And that's the last homework set for the course. The TAs will grade it and then they'll return it. And then you have your final exam. Okay, so I won't prove that. So now 1 and 2 are done. Now 2 and 3. That's again sort of fairly straight. 2 and 3 is easier because there is no such fancy identity and everything. But it's just the properties of linear products and the adjoint map. So let's see, which one did I write down first? I wrote down 3 implies 2. Okay, 3 implies 2. Let's see. So now I want to prove 2, so I write down PV, TW. Okay, so now I can take the T on the other side, so it's T star T, D, TW. But T star of T of V is the same as first doing T star compose T, applying it to V. And now by 3, T star T is the identity, D and W. Identity applied to any vector itself, so you get V comma W. And you're done. 2 implies 2. And similarly, if I had T star, then I would, instead of taking the T here to there, I would take the T. Oh. Okay, no, so this one I should not write. This may not even be. Let's not write this down. Then I have to talk about TT star also. Let me do it later. Yes, let me not do it. So cancel this. Okay, fine. Next comes, so I would like to use finite dimensionality in that case. Okay, 2 implies 3. Okay, so now I know this is true. Why is this true? So let's look at, so to prove that 2 linear maps are equal, you prove that T star T at V equals identity at V. And then by the homework problem, evaluate against something W is the same. So let's just do this. So T star T, let's start from here. So T star T V apply this map, evaluate at V, and compute against W. On the one hand, this is equal to now I know property 2. So I know that this is TV TW, and hence it is VW. So this left hand side equals this right hand side for all W. For all W in V. How can this V star T of V minus V be 0 against all W's? By the homework problem, this is implies by the homework problem T star T of V equals V for all V in V. But what is the linear map which sends V to V? There's a unique such linear map and it's called the identity map. Finally, the proof is complete. So 1, 2, and 3 are all equal. Okay, and so such maps are called unitary. That's fine. Obviously, when V is finite dimensional, if T star and T is identity, then T times T star is identity. So note, if V is finite dimensional, then T star T equals identity is if and only if T times T star is identity. That's the fourth equivalent condition if V is finite dimensional. Okay, so these are linear transformations which are unitary. I think I now want to talk about the matrices themselves. Let me see. Am I forgetting something in between? No. So from linear maps to matrices. Yeah. Okay. Great. Once we do this, we will get to the. Yeah. So we'll talk about the basic properties of orthogonal matrices and unitary matrices. Once we do that, we will get to the defining normal operators, write down the spectral theorem, and I think that's where we will stop today. And next, the last class, we will just simply prove the spectral theorem and end the course. Okay, so from linear maps to matrices. Okay, sorry for cutting. Okay, so definition. Basically, yeah. A matrix is. I'll just write down the definition in parallel. A matrix A belongs to C to the n cross n is a square matrix. It's unitary. If A star equals A inverse. I think that's what it is, A inverse. This is if and only if A star A is identity or A star is identity. And similarly, a real matrix A in R to the n cross n is orthogonal if A inverse. Now I don't need to take star because it's conjugate transpose, but everything is real. There is no need to take conjugates. Sorry. Yeah, I just need to take the transpose. And of course, as I said, so that's why this is exactly the same as A star because it's real. So unitary matrices, orthogonal matrices are a special case of unitary matrices. And now the basic lemma is, of course, that let's write in the basic lemma about these matrices. So these are exactly the matrices, or these are exactly the linear transformations which are unitary or orthogonal with respect to the standard basis. Okay? And I'll write this down. These are precisely unitary or orthogonal maps on F to the n and this is the standard inner product. Which means with respect to the coordinate basis. Sorry, the standard basis. That thing is just summation AI bi or AI bar times bi. That is the standard inner product with respect to the standard coordinate basis of Rn or Cn. And that the orthogonal maps with respect to that inner product are precisely the orthogonal or unitary matrices. It's just the standard inner product with the standard basis. Then it gives you the matrices themselves. Okay, great. So that's that. So now, okay. Now we continue. So basic lemma. Basic lemma. Okay, so first of all, and this one is also a problem. So say A, B, and C to the n cross n, unitary. Actually, I should have read. No, I should have written one more thing before lemma. There is a name for the collection of all unitary matrices and all orthogonal matrices. So definition. This was part 1, part A and B. So see, U of n is the set of all A in C n cross n unitary. And O of n for unitary and orthogonal. These are the definitions. A belongs to R to the n cross n orthogonal. Okay, so now basic lemma. Property 1, U of n, O of n are closed under multiplication and transpose. And also under conjugate. So I take any matrix in either this set or in this set, I take its conjugate or I take its transpose, I get back a matrix in the same set. Of course, if I take the conjugate of a real matrix, I just get back itself. And also, if I take two matrices in this set or two matrices in this set, oh, one more thing. Conjugate, transpose, and inverse. Okay. So maybe I should say that. So clearly, okay. First of all, clearly this is contained in it, right? So maybe I should first say this is to be property 2. Property 1 is that all the matrices here are inverted. So there is no question that the inverse exists. Okay, so 1, A belongs to U of n implies A inverted. And because the orthogonal matrices are contained inside this, the same is true for A belongs to O of n. The second now is the second property is that these two sets are closed under multiplication, conjugation, transposing and inverses. The third property, what is it? There is a third property. Yes, a matrix is unitary. So in particular orthogonal, A belongs to U of n, if and only if the rows or the columns of A form an orthonormal basis of F to the n, of C to the n. And similarly for O of n, the rows, columns of A form an orthonormal basis. Okay, and similarly, of course, you have 3 prime. I won't even call it 4. A belongs to O of n, a real matrix. If and only the same thing, orthonormal basis, the rows and columns form of R again. Okay, so that's the basic lemma. And so it's very nice. The orthogonal matrix, these are exactly the ones where all you do is you take an orthonormal basis of F to the n, F is R or C, put those column vectors together, and you get an orthonormal matrix, and you get an orthogonal matrix or unitary matrix. It's exactly the same. Okay, great. So now let's prove this thing, and then go on to normal matrices. So first of all, why is it invertible? This is sort of trivial. If it's unitary, then A inverse is A star, so that's obvious. Or if in, yeah, actually that's just obvious, or by definition, or if you take, if A is unitary, then A times A star is identity, and yeah, and then you can talk about, then that gives you that it's full rank because it's a square matrix. Okay, second. The real parts are 2 and 3. So the second is actually a homework, so I won't even mention it. It is a homework this time. The third one is what really matters. So let's see. This is actually just directly written out, I think. If and only if, yeah. So A is unitary. Okay, then let's first write down the columns. So write down, write A equals V1, V2, Vn. These are the columns. So what is A star? V1 star, Vn star. Okay, let me look at A star times 3. So now A is unitary. So I take A star times, I can do this or I can do A star times A. And from that you can derive it. So A star times A is identity. I'll take that one instead. But what is A star times A? And this is again where the whole trick of working with partition matrices works. I just think of these like as if they are scalars. This is like n cross 1. This is 1 cross n. Something is wrong. Sorry. This is 1 cross n. This is n cross 1. So the whole thing, this will be n cross n. And what are the entries? The entries are V1 star V1, V1 star, I think first row, second column V2, V1 star Vn, V2 star V1, V2 star V2. You get it. V2 star Vn. These are all scalars because they are all inner products. Oops, something is going wrong here. This is Vn star Vn. This is Vn star V1 and Vn star V2. Okay? This must be the identity matrix. But what is V star W? Remember, that was exactly the standard inner product. So what this is saying is, well, the identity maps these things, the diagonal entries are ones, and the remaining entries are zeros. That is exactly the definition of an orthonormal basis. Vi star Vj equals, sorry, Vi star Vj, but that is the same as Vi inner product Vj in the standard inner product. And this is equal to delta Ij for all I and j. So how can it be that Vi inner product Vj is delta Ij? That's if and only if it is an orthonormal basis. So this is how you prove that this is if and only the columns form an orthonormal basis with respect to the standard inner product. That was the. So I should have really said Cn and and the standard is on the orthogonal basis of Cn. Actually, this proof entirely goes through in Rn as well, where all the stars just mean transpose, but it's nothing wrong to say star even in Rn, because you're taking the conjugate of a real number, so you're not changing. Okay, so these are the basic. This is the basic lemma on unitary matrices and orthogonal matrices, and that finishes the part about unitary and orthogonal matrices. Now I need to define for you the normal matrices, state the spectral theorem, and we are done. Okay, so yeah, now not much left, maybe around 10 more minutes left in the lecture. Yeah, that's right. Yeah, I can't finish. So normal matrices. Definition, a matrix. So it's again, these are again square complex matrices. They could be real, of course. It's normal if A star. So you have a matrix, therefore you have its conjugate transpose, and now you can multiply them in either order. And if those two are equal, then the matrix is said to be normal. Okay. And similarly, this is probably definition 1. And you can talk of a normal linear transformation in the same way. Let V be an inner product which is space which is finite dimensional, and T is a linear map from V to D. Okay, sorry. We say that T in lin VD is normal if exactly the same condition holds. T times T star. So again, because this is between finite dimensional inner product spaces, finite dimensionality means you can define T star and then you can compose, and that's exactly the statement. These are the definitions. Let me give you some examples. So for example, unitary matrices are normal because both the products are identical. Yeah. So let's do a bunch of examples. First of all, the identity map is normal because the identity times identity star is identity. Okay. Now there are two ways to generalize this. One is to say that yes, the unitary map, the identity map is unitary, and in fact any unitary map is normal. And the unitary matrix is normal, sorry. Let's call it identity N. Because it's finite dimensional, I can talk about this thing. And so that's the only reason that if it's finite dimensional, any map also I can say, but in general, let me just say unitary matrix. Okay. Second is if I take diagonal matrices. Let's say so V equals Fn. F is of course real numbers or complex numbers, and A is D is diagonal matrix. Well, then this is clearly normal also because the diagonal matrix, what is the D star? It is also diagonal. So you just have products of two elements, and then this is clear. Implies D is normal. This is trivial to verify. The next one is just like this thing, that if I say that something is diagonal has a nice property, like distinct eigenvalues, then diagonalizable maps with some kind of P inverse also have distinct eigenvalues. Except now, I need to again sort of change bases in an orthonormal way. So I don't take PDP inverse, I take a unitary times D times a unitary inverse. Okay, so that's a thing, my third example. Yeah, so again B is Fn, D is diagonal, and then A is either unitary or orthogonal. So it depends on F. If F is R or R, then if A is orthogonal, if F is C, then A is unitary. Sorry, this is not A, this is U. Oops, my mistake. And now, like PDP inverse, I do UDU inverse, except U inverse is the same as U star, whatever. So that's what we write. Okay, I think that's it. Then A equals U du inverse equals U du star is normal. I'm going to prove this. So in particular, because the identity matrix is unitary, therefore example B follows from example C, and we will prove example C right now. We're almost at the end. Proof. I just have to check that A star and A star be equal. So proof. Say, let's say D is lambda 1, lambda n. Then A star, let's say A star. That is U, D, U star, U, D star, U star. Right? Very good. But now you see, the U star and U are inverses, so they cancel. This is U, D, and now D star is the conjugate transpose. But what is the transpose of a diagonal matrix? It is itself. So, this is just the conjugate times U star. But what is D star? This is U times mod lambda 1 square, mod lambda 2 square, mod lambda n square, times U star. And you can check that this is exactly the same as U d bar D times U star. Because these things in between, whether you multiply this way or that way, you always get lambda and mod lambda square. But then that is exactly the same as this is U d bar, and again I can insert now U star U in between, d U star, and I can arrange the multiplications associated. So I can multiply in this order. But now look at what is this. This is U. First of all, I can say d star U star times U d U star. Because d bar and d star are the same. Right? The same thing that we have heard about. And now, oh, I never told you what was it. A star is what it is, U, D, U star, star. I should have calculated this first, my apologies. What is A star? Okay, but now this is the exact thing we have seen already. Basic properties of adjoints. If I multiply matrices or compose transformations and take star, I get the star of all of them, but in the reverse order. So you get, first of all, I get U star star. What is U star star? It is U. That was another basic property. Times D star times U star. U star. That was what was here, and that was being used here, and now that is again being used here. This is A star. This is A. So A star equals A star. So that is what we have. And therefore it's normal. Great. Okay, so with these preliminaries, let me end today's class with the main theorem, the final main theorem of the class, of the course. The spectral theorem. Okay, and this is yeah. Okay, so 1. Again, so a matrix A. So what does this say? It says that if you have a diagonal matrix and you have a unitary matrix, and you write down A to be of this form, then A is normal. The spectral theorem says that the converse is also true. If you have any normal matrix, then you can find a diagonal and unitary matrix such that A is on that form. A matrix A in C to the n cross n is normal if and only if A equals U d U star. For some D diagonal D n cross n diagonal and U in U of L. Unitary. And so this way, this implication is being proved over here. So I gave you a proof, and there was a reason why I gave you a proof. That was part of the proof of the spectral theorem. The main, of course, the harder part is this other way, and that's what we will prove next time. Say A is normal. Then A equals A star. A is its own adjoint. If and only if all of the eigenvalues of A are real. By the way, I should point out, not all complex normal matrices need to have real eigenvalues. If you take any complex diagonal matrix, then those complex entries are the eigenvalues, and yet the diagonal matrix is normal. So it's not the case that every normal matrix has real eigenvalues. Only the ones which equal their own adjoint have real eigenvalues. And the name of such matrices is called Hermitian. Okay, so I think that's where we will stop. Yeah, maybe I'll just give you the definition. So here, definition A is Hermitian if A equals A star. So the spectral theorem ends here, of course. So A in C to the n cross n is Hermitian. It is not named after Hermit, but Hermite, Hermite. IAN is Hermitian or Hermitian. If A equals A star, and I think skew Hermitian or something, yeah. So A star equals A, maybe I should say it that way. A star equals A, and then skew Hermitian. If A star equals minus A. Okay, so that's just the definition. So basically, what we are saying is a normal matrix is Hermitian if and only if all eigenvalues are real. Okay. Of course, for other matrices, this is not the case. For instance, I could take like 1, 1, 1, 0. This is all eigenvalues are clearly real, but this is not. You can check it's not normal. It certainly is not Hermitian, right? It's not A is not A star or A transpose. So this is only true for normal matrices. The normal matrix is Hermitian if and only if all eigenvalues are real. Okay, so I think that's it for today. So we have stopped with the spectral theorem. We will so next time we will not immediately prove this theorem. We have to first develop some preliminaries, and the preliminaries are that for a normal matrix, right, the eigenvalues, the eigenspaces of A and A star are the same, except the fact that if lambda is an eigenvalue for A at a certain space, then lambda bar is an eigenvalue for A star at the same space, at the same vector. So we will first prove a few of those properties, and using those properties, we will prove the spectral theorem, and then that's it. Okay, that's it for today.